All right. Let's see, is that ours? There we go. All right, did we get to this slide last class? Maybe, like very briefly. We'll start here. It's fine if we're recapping some stuff. So, from now on, the rest of the chapter, we're going to focus exclusively on chemical reactions that are at constant pressure so that we can look at the heat by looking at the enthalpy, right? So enthalpy is this specific kind of heat that happens at constant pressure. We're also going to only pay attention to ones where work isn't being done, which means that all of the energy exchange that's happening in the chemical reaction is going to be through the absorption or release of enthalpy, or this special kind of heat, okay? So remember, it's written right there. So enthalpy is heat at constant pressure, and we're gonna talk about reactions exclusively where we can look at enthalpy, okay? So, 2 versions. First one, we label it as exothermic, exo meaning like exit. So heat is exiting the reaction or the system, and endothermic is where heat's being absorbed. And then I have these like kind of reminders about all of the things that you should be aware, or that are signs that we're talking about an exothermic reaction. So a lot of the times you're going to be given a chemical equation, like if you look at this page here, you're going to be given a chemical equation and have the enthalpy just reported as a number, okay? So sometimes that's all the information you're given, is that the enthalpy is negative. So what you can, or what you should be able to infer from that, is that if you have a negative enthalpy, that means that energy is being released, or specifically heat is being released. If energy is coming off, that must mean that there is a loss in energy from reactants to products. Or another way of saying that is that the products are at a lower potential energy than the reactants are. So that's this one here. Physically, this will register as warm in the surroundings because that heat is coming off, and either you'll measure it like with a thermometer, or you'll physically feel that it's warm. And then we aren't going to talk about like the other part of this story of thermodynamics, which is called entropy. It's like the other factor that helps us know whether or not a reaction is going to occur. But this one is always going to be kind of our favorable reaction. Like if the enthalpy is negative, that is a good indicator that the reaction is going to occur, because it's going to a lower potential energy, right? We've always said things tend towards a lower potential energy. So if I drop the pencil, or if I let go of the pencil, it's going to drop, right? That's lower potential energy. The endothermic version should be a little bit weird because it's going up in potential energy. So that's like if I had the pencil sitting here and it went up. It's not going to happen with gravity, right? This other concept that we're not going to get to, entropy, is what allows this process to happen, because there's kind of like 2 things that are dictating the overall likelihood for a chemical reaction to occur. And we're just talking about one component. So that's why this is okay, why it actually might happen at some point. Okay, and those ones would have a positive delta H, heat's going in, so you're increasing in energy over the course of the reaction. That one would feel cold, or you'd measure a drop in temperature, because you're not measuring the reaction itself. This always confuses people. They're like, well, heat's going into it, so shouldn't it feel hot? You're not feeling the reaction, you're feeling the surroundings. And even if energy is going into it, it's not staying as heat once it goes into the reaction. It's being used to break apart chemical bonds. So it's being used to lift that potential energy. It's not just going in and staying as heat. And then the last thing that we haven't really had a whole lot of time to talk about is where this change in the potential energy comes from. So these ones right here talking about releasing and forming bonds. I'm just going to go to the next page where I have a little more room to write and show you what I'm talking about there. Okay, so I'm going to use this reaction down here as an example of what I mean by the breaking and forming of bonds thing. So if you want to reference back to it, you can. So in that reaction, we already know that one said it releases energy, right? In that reaction, it showed us propane, which looks like this. And it reacts with 5 oxygen molecules. I'm just drawing these out to make a point. Okay? And then it produces CO2 and water. So for those, we'll just write, I think it was, 3 CO2s? Yeah, and 4 waters. Okay, so for this reaction to occur, we have to break this bond, that bond, that bond, that bond, all of these bonds. We have to break them apart. That's going to take a certain amount of energy. Okay, so break reactant bonds. That's going to take energy. So why then is this reaction have a negative enthalpy? Why is energy released overall? Because in the products, you're forming new bonds. And that's going to release energy. So when we draw these energy diagrams, it's really most accurate to include this like hump in the middle, because that accounts for that energy that's required to split those bonds up. So when you initially go up in energy, now this isn't perfectly right, so if you learn later that there's more to it, that's because there is. But when you initially go up in energy, that's because you're breaking those bonds. And then when you go back down, that's you forming the bonds. And it's just that in this case, for the propane, the energy that's released when the bonds form is greater than the energy that it took to break them up. So overall, there's more energy released. Now, when we look at the actual change in energy, we don't worry about that middle step. We just look at what's the products, what's the reactants, and how do they differ. Because like this chunk of energy there, that's already compensated by the amount that's broken. We just want to know how much overall is gained. Okay, so when we look at exothermic reactions, that's why it says here, more energy is released when the bonds in the products form than was required to break them. In an endothermic reaction, it's the exact opposite. So you've got all of this energy that's required to break those bonds, but you don't release nearly as much. So that's why overall energy has to go in, because it just takes a lot more energy to break up those bonds than you get out in the process. When you guys talk about activation energy, if you've talked about that in biology classes, that's that hill there. That first jump in energy, that's the activation energy. You have to put in a little bit to get things started, to start breaking up some of those bonds.
So does endothermic form and then break, or is it?
No, it should bother you. So this other factor, entropy, you can kind of think of them as like two different kinds of potential energy. And this one type has an increase. The entropy, though, will have a very big decrease. And so it will kind of outweigh that fact that it goes up in energy. Because if it was only this, you're right, it couldn't stay like that. It would just reverse back. But there's like these two different types of energy that allow this to occur. So in this case, the change in entropy has to outweigh this one. It's really a very interesting concept. It's unfortunate we don't have time for it, but. Okay, moving along. So when we look at a chemical reaction, the ones we're gonna look at now would be considered balanced thermochemical reactions. So they'll include the change in enthalpy, just like this one does. So when you see this, you need to make sure you realize that the enthalpy value that's listed there is for these specific amounts that are listed in the balanced chemical equation. So like for 1 mole of propane and 5 moles of oxygen, that reaction will release negative 2,044 kilojoules, okay? If it was a different amount, it's going to release a different amount of heat. It scales just the same way that moles would. Right? Like if I have 2 moles of propane, then I'm actually going to make 6 moles of CO2, right? And the way we used to figure that out is with mole ratios. And we would say for every 1 mole of propane, I can make 3 moles of CO2. Or for every 1 mole of propane, I use 5 moles of O2. Now we're going to add enthalpy values in there as another, what was the term I'm missing? I just had it in my head. As another component. In fact, if it's negative and heat's being given off, you can think of it as a product. So I'm even going to write here like plus heat. So heat can be treated as a product in an exothermic reaction. And the amount of it is in the ratio that the balanced chemical equation is in. So like I've written down here the conversion factors. So just like we would have 1 mole of propane for every 5 moles of O2, so it's very similar to that, we're going to write it like this for the amount of heat. For every 1 mole of propane, you release that amount of heat. So for 2 moles of propane, you're going to release twice as much heat. You're going to release 4,088 kilojoules. So go ahead and do that. Use this practice problem and determine the energy released when it's 3.45 moles of propane. And I'll finish my yogurt. I'll probably put this in 3 sig figs since that's what the mole value is in. Now, you may have just looked at it and been like, well, duh, I just multiply the 2. That's fine. But like if it was, let's say, 3.45 moles of oxygen, that's the point when like you probably need to consider the ratio, because now you're talking about that many kilojoules per 5 moles of oxygen. Okay? So just keep that in mind, that it's not always just super straightforward. You might actually want to use the ratio. So this is just like another add-on for stoichiometry. Good? Okay. All right. So the rest of the chapter, this is a summary of the rest of the chapter. So we're going to do the first one today, which is determining enthalpy experimentally. So this is identical to what you guys would have done in the lab in Chem 1. Then we're going to look at 2 different ways to calculate enthalpy. So we have some unknown equation, and instead of doing an experiment, we're going to use data that other people have done years and years and years ago, and it's tabulated in books and stuff. Books, the internet, whatever. We're going to use that data to calculate an enthalpy for a reaction we want to know. So we'll start on number 2 today as well, and then kind of pick up there and do another example or 2, and then do 3 on Monday. Okay? So we'll do half of these and then the other half on Monday. I would encourage you guys to do some of the homework over the weekend, because like it's just going to get a lot if you try to wait till the end of the chapter and then it's due, I think, Tuesday night. That would be a lot to do all at once, okay? So try to do a decent amount of the homework. In actuality, if you're feeling comfortable with the stuff today, then there's only really one type of reaction or of calculation that you wouldn't be able to do, which is this last one, okay? All right, so calorimetry. Does this look familiar from lab? Those of you that took lab last semester? Yeah? Okay. All right, so you have a reaction, you stick it in a coffee cup to insulate it, okay? And you perform the reaction in a liquid. Usually it's just mostly water. It's going to probably have some spectator ions in it. I think in this example it's sodium. Sodium doesn't actually participate in the reaction, so it's not considered part of the reactants and products, but it does end up affecting like the specific heat of the water. So that'll be a little bit different than just plain old water. Then you measure the temperature. As the reaction occurs, you record that initial temperature, the final temperature, and then we use this same idea as we did when we were looking at that chunk of metal in the water. Remember, we looked at how the heat was transferred? So if you remember, in that case, we didn't know what the metal was. We couldn't directly calculate the heat that the metal lost, but we knew what the water was, and so we could calculate it for the water and then say the metal is going to be the same number, just opposite sign. So we're going to do the same thing here. We're going to calculate it for the solution, SOLN there at the bottom is the solution. So we're going to calculate it for the solution, which, like I said, is mostly water. And then we'll know that the reaction is the same value, just opposite sign. Okay? There does get to be a little bit of weird math at the end because it wants to know it for a balanced equation, not for just a small chunk of the reactant that we used. So we'll have to kind of do a little bit of math to basically get it in the right units. Okay, so I want you to take a minute or so and orient yourself to this question. Make sure you get like what's going on. You can draw yourself a picture if you want, or like highlight some of the key information, but I just want you to take a minute to read through it and make sure we're all on the same page. My watch keeps telling me that I'm stressed. I did this last class. Does anyone else's like smartwatch have that thing? It's Fitbit, so I think it's like overly sensitive to my health. But it keeps being like, how are you feeling? I noticed some changes in your... I'm like, I'm trying to get through a class. That's how I'm feeling, okay? Trying to make sure they learn it all. All right, so I'm going to draw our little reaction vessel here. We've got some solution in here, and we're going to measure the temperature. And the solution starts with 2.57 grams of acetic acid, but the whole mixture is 155 grams. And they're also telling us that the heat capacity is, so C is 4.12. So you'll notice it's close to water's. Water is 4.184, but not quite the same. That's because we have other ions that are mixed into there that are affecting how water is going to absorb that heat. So that's why they have to give us a different specific heat. Okay? And then we put the acetic acid in with the NaOH, and they react, and we see a temperature change of 22.4 up to 26.1. So before I even do anything, I can tell that heat is going out of the reaction. Okay? So I know that this guy is exothermic because the surroundings is warming up. So when I report that delta H, I know it should be negative. Now, this is like where I'm interpreting the sign based on the concept. I'm going to do the math now, and it's going to be the same. So, like, both of them should match, but it's good to be able to do it from both sides. Like, if you were given a problem similar to this, it would probably have less data, but it said, like, you notice a temperature increase. Is the reaction exo or endothermic? You're not going to want to go through and do a whole calculation just to determine that, right? You're going to want to be able to notice, okay, that's the temperature of the surroundings. It's increasing, therefore it's exothermic. The thing is giving off heat. Okay, so we're going to go ahead. I'll start this on the next page. We're going to go ahead and calculate the Q of the solution, because I know that when I want the reaction, I'm just going to do the opposite sign of that. And that's going to be, and I'm going to like write these subscripts to just really emphasize, we're talking about the mass of the solution, not the mass of the acetic acid. That's part of the reaction itself, just the mass of the solution, the specific heat of the solution, and the change in temperature of the solution. Now, it's not wrong if you just write MC delta T. Just make sure you're putting in the right pieces of data there. All right, so why don't you guys go ahead and plug these in and calculate the Q of the solution. And then just change the sign for the Q of the reaction. I'll give you a minute and then I'll start working it up here as well. Okay, so feel free to check your work once you're done. I gave myself 4 sig figs because the 155, all of them really are in 3, but I'm not actually quite done yet, so I don't want to round off completely. Also, make sure you note that like these usually come in joules because the specific heats come in joules per grams degrees Celsius or joules per mole sometimes. And so I'm going to actually end up needing to convert this. So if you notice in the question, it says, find the enthalpy change for the reaction in kilojoules per mole. That's because the balanced equation has 1 mole of acetic acid. That's why it's asking you to find it in kilojoules per mole, because it's for 1 mole of acetic acid. If the balanced equation had 2, then you would just be finding the enthalpy for the balanced equation, or for 2 moles for that matter, okay? So what we have right now is joules, and it's actually joules for how much? 2.57 grams of acetic acid. Okay, so that is not per mole, and it's also not in kilojoules. So what we need to do is convert this into kilojoules and moles. And then, we've talked before about like if you have a unit over another unit, that's a conversion factor. If it says kilojoules per mole for the answer, that means you need to find one, find the other, and then just divide. Okay? So we're going to convert the joules into kilojoules, which is quite easy, right? Take this, I'll write it out just so we're all clear. 1,000 joules per 1 kilojoule. Okay? So that's 2.363 or negative 2.363 kilojoules. Which, okay, good, it's negative. That's what we predicted as well. Don't forget. But then we need to do this per mole, and we have the 2.57. So we're going to go ahead and, go back to the recesses of our brain in chapter 3, I think it is. And we're going to convert grams of acetic acid to moles. So I believe the molar mass is 60 something, 60.052. All right, so that comes out to be 0.042, let's do 4 sig figs again, 280 moles. So definitely not 1 mole. So to determine kilojoules per mole, we're going to take the kilojoules and divide them by that number of moles. So that will give us the value for 1 mole. Negative 55.2 kilojoules. Now that's for 1 mole of acetic acid. The way I'm going to write it up there is for just that's how many kilojoules for the reaction, because it's for 1 mole, but that's because that's what the reaction says. That's why we calculated it that way. Okay, so a few different steps when you approach a problem like this. The nice thing is that these are almost all identical. Like there's quite a bit of variation in the next 2 types. Like just little different things. You might have to practice more of them to get a handle on it. These ones, they're all going to look pretty much like this. Okay? So if you get into the homework and you do like one of these and it makes sense, great. You're pretty much done. If you get a couple wrong, you need to make sure you can figure them out. But you don't have to see a lot of different ones in order to get enough practice for these guys. All right, any clarifications on this before we move on to the next type? Is anyone happy to be back to math? Okay, good. Okay, so the next ones, if you like Sudoku, this is kind of like Sudoku. It's like a little bit of a puzzle you have to work through. So let me skip ahead. We're not going to do that. Let me just skip ahead and show you what the problems are going to look like, and then I'll show you the methods we use to solve it. Okay? So you're going to be given a reaction, and you don't know the enthalpy, just like before. You're given, the calorimetry one, you had a reaction, you had to determine the enthalpy. The difference is here, instead of giving experimental data, you're given other reactions that have similarities with the one you're looking for, but they're not the same, and you know those enthalpies. Okay, so it's like, hey, we all know, it's a very known quantity how ammonia breaks down into nitrogen and hydrogen gas. So that's something we can easily look up. In your case, you're going to be given all the reactions you need, but they are well-known reactions. Okay? So what we're going to do is we are going to attempt to manipulate these reactions. And by manipulate, I mean flip them around, reverse them, products to reactants, maybe multiply their coefficients, maybe add them together. Like, we're going to do all these manipulations to them to try to make them look like the reaction we want. So we want to make them look like 2 moles of N2 and 6 moles of H2O reacting. Okay? And the reason we can do that is because enthalpy is a state function. So we don't actually care if the steps we go through are really happening in the chemical reaction, as long as they get us to the final spot and they're the same. Like, as long as the starting spot is the same and the final spot is the same, we don't care how we get to that point. So, for example, this blue arrow here is representing like the reaction we want to know the enthalpy for. We want to know A plus 2B goes to 2D. What's that enthalpy? In order to find it, we're going to use different equations, like 1 and 2, that are labeled here. Maybe A plus 2B goes to C, so we know that. And then we know C goes to 2D. So instead of figuring out this one, we're just going to combine these two and say they work to get us from the initial to the final, and that's all we care about. Okay, so that's why this method is allowed, is because enthalpy is a state function. It doesn't matter how it gets there as long as we end up in the same place. That's a math thing. What is that, like the something property, the transitive property? I don't know. The like, if you just cancel out, let me write it out actually so you see what I'm talking about. A plus 2B goes to C, and then C goes to 2D, right? Then you're canceling out C. C is like just kind of the middle thing. And then you can say A plus 2B goes to 2D. This would be equals instead of an arrow if you're talking math, but it's the same thing. Commutative. I think that's it. I think it's the commutative property. I know math really well, but I don't know the terminology. And like proofs, probably couldn't do those anymore. Okay, so when we take known equations, like I said, we're going to have to manipulate them. So we need to know the rules about what's involved when we manipulate them. So first point, if you multiply it by a factor, like a number, you have to do that to everything in the reaction and to the enthalpy. So the example here, carbon plus oxygen goes to CO2. Okay, so if I want 2 carbons, I need to multiply everything through by 2 and multiply the enthalpy by 2. If I had this one down here at the bottom, I can do the same thing. It's not like the coefficients all have to be 1. If I want to multiply that by 2, I would do 2 C3H8 plus 10 O2 goes to 6 CO2 and 8 H2O. And then my enthalpy would be negative 4,088 kilojoules. Okay? So if I multiply a reaction through, I've got to multiply the enthalpy. You can divide as well. So if you had a larger value, you can divide as well. Just do the same thing to the enthalpy. Then the other thing is if you flip it around. So in this case, I turned the reactants into products and the products into reactants. So now instead of making CO2, I'm starting with CO2 and making carbon and oxygen. That just changes the sign. Okay, the amount of energy change is the same. It's just now it's absorbing it instead of releasing it. So when you flip it around, you're flipping the sign. Think of it that way. Okay, so that's actually all you need to know about how to manipulate them. Now we need to actually just do it and practice it. Okay, so the way I want you to approach these is look at your unknown reaction. You know the reaction, you just don't know the enthalpy. So look at the reaction that you don't know the enthalpy for and start with the first compound in the list. So 2N2. So I need to somehow manipulate those two reactions that I say are known. I need to manipulate them to get 2 nitrogens on the reactant side. So when I skim through my known reactions, the only place where I see nitrogen is right here. Right? It's on the product side though. It's also only 1/2 mole, and I need 2 moles. So I'm going to have to do 2 different types of manipulations here. First, I'm going to turn it around so that it's on the correct side, on the reactant side. Okay, so again, restating, I'm manipulating these reactions because I know their enthalpy values. I'm going to manipulate those ones to try to eventually add them together and make them look like the one in the box, the one I'm looking for. So I'm going to flip reaction 1 around, and I'm going to rewrite it as 1/2 N2 plus 3/2 H2 forming NH3. Now you will see fraction reactions here. This is like one of the few times where we do that. It has to do with how the values are reported when they're tabulated. So don't let that bother you. As long as you're changing the enthalpies along with it, it's just fine. Okay, so the new enthalpy value here is the same value, just a different sign. So negative 46 kilojoules now. Okay, so it's a first start, but we didn't want 1/2, we wanted 2, right? So I need to multiply the whole reaction now by 4 so that I get 2 moles of N2. So I'm going to take this and multiply it by 4, which means I'm also going to have to multiply the enthalpy by 4. So I get 2 moles of N2. Oh no, I have to do fraction multiplication. It's going to be okay. Multiply the top number, divide by the bottom number, all good. So 3 times 4, 12, divided by 2 is 6. So 6H2. And then 4 NH3. Okay, my new delta H is 4 times that. 160 plus 24, negative 184 kilojoules. Okay, we did this whole thing so that we could get the 2N2, right? So I'm going to highlight that to be like, that's the reason why we did this. We wanted 2N2. And I got a lot of other stuff with it, but don't worry, I'm going to give you the reactions you need, and only those, and you're not going to have extras. It will work out. There's always a way to work these out. It's not like you're going to leave something behind. Okay, so now I look at my next chemical in this unknown reaction, 6 H2Os. I want 6 H2Os. Okay, I'm looking at my reactions. Reaction 2 is where I have 6 H2Os. Let me also I'm going to cross out this guy because we didn't actually use that, right? That was just kind of like we did one step and then we did another. Okay, 6H2O. So I need my second reaction. Same thing that happened last time. It's on the product side. We need it on the reactant side. Also, there's 2 moles and we need 6. So what I'll do when I notice that is I'll just write near the enthalpy, I'll say times -3. Because I'm telling myself I need to flip it, that's the negative, and then I need to multiply everything through by 3. So I make note of that, and then I go do that manipulation. So instead of doing this in 2 steps this time, I'm just going to do it all in one. So I'm going to flip it around and multiply by 3. So I get 6H2O, which is what I wanted. And then when you do this, make sure to line up the arrows, because eventually you're going to be adding these reactions together, and you want to make sure you're clear on what's on the reactant side and what's on the product side. Okay, so 6H2O, and then on the product side, I'm going to have 6H2 and 3O2. And my enthalpy there is, I'm not going to do that one in my head, -484 times -3, or 1,452 kilojoules. Okay, so that got me my 6H2O. So I'm going to highlight that just so I remember. Good, I got my 6H2Os that I wanted. Okay, so another way, I'm going to check off, got my N2, got my H2O. Now I look at the next one. I need 3 O2s. I don't have any more reactions, though. That's annoying. Oh, wait. I have all this other stuff in the reactions that I already did. Can I use that? Like, is that going to help me? Sure. I have 3 O2s right there. So you don't get to, like, create these 6H2Os without all the other stuff that comes along. So sometimes the other stuff that comes along is going to be good. It's going to be what you want. And sometimes it's going to be stuff you don't want. And in that case, it would have to cancel out by the time you get to the end. Just like in that earlier example with the letters, we saw that C canceled out. That's the kind of thing we're looking for. Okay, so we've got our 3 O2s. And now we need 4 NH3s. So since I don't have any new equations, I'm hoping, yes, there's my 4 NH3s. So in the process of manipulating one of them, I got actually 2 things out of it. And then hopefully you're seeing too that the 6 H2s that are on reaction 1 and then also on the product side on reaction 2, those now get to cancel each other out. So all I'm left with is the things I wanted. So the last step is I sum them together. So 2N2 and 6H2O, and they make 4NH3 and 3O2, and then I add their enthalpies, because whatever I do the reactions, I have to also do to the enthalpies. And the enthalpy there is 1,268. And that's this value, the thing we were looking for, the enthalpy of the unknown reaction. So you're going to have to do a lot of these because you need to see, like, you need to practice the method. And also there's like little, it's kind of like balancing equations. There's little tips and tricks. So before you leave, let me just show you one trick on this one because it has a good example. So this is the one we don't know the delta H for. If I look at H2 and I say, okay, I want 1 H2 on the reactant side. I look through my things, reaction 2 and 3, they both have H2 in them. If you see that happening, just skip it. Don't do H2. Move on to Cl2. Okay? Because there's something similar to this in balanced equations. If you try to like manipulate the oxygens when they're in the carbon dioxide and the water, they just start like bouncing off each other and it gets confusing. So don't do that here. Skip the H2 because it appears in 2 different reactions. Just move on to the Cl2. Okay, so we'll start with this one on Monday and do 1 or 2 more practices and then do the third type. Have a good weekend.